Okay, here is the answer key for question 2 of the 2020 practice exam. Okay, and I'm going to present my entire screen. Share it. Okay. I'd like to share my screen. Okay. So, presenting to everybody. Here is question 2, and here is my document that I've prepared with my AP ID at the top, my initials, and page 1, question 2A clearly labeled. Okay, so for A, write the chemical formula of a species that behaves as a catalyst in this mechanism. So what a catalyst is something that's present at the beginning and at the end of the reaction. It's not used up in between. So it's present there and present at the end. It's different than an intermediate. An intermediate is made and then used. So if you guys can see, this right here is made in step 1. It is used in step 2. The HCONH2 right here is made in step 2 and used up in step 3. So those are intermediates. Those are not a catalyst. This guy is present at the beginning of the reaction. It's needed here at the beginning, but it is not in the overall reaction. So that makes CH3. And the trick to do the subscripts again is control comma for subscripts. So if you want to practice that, or if you just want to write it out because you're faster at writing. Okay, so that is our catalyst, and that's the answer for A. For B, according to the proposed mechanism, if additional NH3, okay, here's the NH3, here's the NH3, is added to the reaction mixture, will the rate of the overall reaction increase, decrease, or remain the same? Justify your answer. So we want to be clear when we state our answer, and the answer is, this is our rate determining step. There is no NH3, so it will have no effect. So we will say the rate of the overall reaction will remain the same. Okay, there's my answer. There's my point. Second part, justify it. Why is it going to remain the same? The NH3, I'm not going to bother with subscripts because they'll know what that means. The NH3 is not present in step 1, which is the slow step. So we're going to call that the rate determining step. Okay, and will therefore not affect the overall rate. Okay, because this is what's slowing it down. If I add something from step 2, that's a fast step. It's not going to speed up the overall reaction because this is the one that depends, that the rate depends on. Okay. All right. Next question. Part C. A student generates the following potential energy diagram. Is the student's diagram consistent with the enthalpy of the overall reaction? What is the enthalpy of the overall reaction? It's right here, capital H, enthalpy. It's negative 81. So your brain should say, or you can even write it down on the side, negative enthalpy means exothermic. Okay. This diagram right here shows the potential energy going up. That means you have put in energy to get up to this level, and that's not consistent. Okay, so is it consistent? The diagram is not consistent with the enthalpy of the overall reaction. Okay, use the same words that they are using down here to clearly state your answer, and now we have to justify. So why? The overall reaction has, a negative enthalpy, which represents an exothermic reaction. Okay. The diagram, however, depicts or shows, you don't have to be fancy, depicts an endothermic reaction because the energy of the products is greater than that of the reactants. Okay, nice and clear, justified our answer. Moving on. Part D, identify the types of intermolecular forces in these two things. Okay, well, first of all, both have London dispersion forces because everything has London dispersion forces. And we have an H bonded to an O and an H bonded to an O. So that means that they both have hydrogen bonding. Hydrogen bonding is a type of dipole-dipole force. So they both have London dispersion forces. Dipole forces. And they both have, just to make it clear, they both have hydrogen bonding. They both have hydrogen bonding. Okay, question answered. Those are the types of intermolecular forces. When equimolar mixture of the two compounds is heated to 50 degrees Celsius in the distillation, the vapor phase contains a higher mole fraction of this. That means there's more of this in the gas phase than the other one. Explain the results in terms of the type and relative strength. So we want to talk about which is stronger, the intermolecular forces. Okay, well, if there is more of this as a gas, that means I'm going to put IMF, let's abbreviate so we can get that done fast. The IMFs in CH3OH methanol are weaker than those in HCOOH. Okay, and why? Why would that be? Just to be safe, let's explain the why. So this is true. The intermolecular forces in this guy have to be weaker than this guy because there's more of it. But can we say, can we explain the why of why is this one more weakly attracted to another one of itself than this one is? So there are two ways to put this. I'm going to give you the best way, okay? Because the CH3OH, the methanol, is smaller. Actually, I'm going to reword it. Because HCOOH is larger. That gives me a better answer. Okay, so because this one is larger and has more electrons, so it is more easily polarized. That is your key. Greater polarizability. I'm going to write it. Polarizability. When you are talking about intermolecular forces, this is our coulombs. Okay, greater polarizability. The bigger it is, okay, the bigger that molecule is, the longer it is. It's going to have electrons that are more easily pushed to one side or the other, and that makes the attraction greater.